So we've established throughout a number of talks throughout today that craton margins and major lithospheric structures are a key region of interest, mainly because they're a great place to focus deformation, fluid flow, and magmatism. So where all the fun stuff happens, really. So key points and take-home messages from my talk, I guess. The Gawler margin with the Campana province is the near-surface expression where a major change happens in the mid to lower crustal compositions. Maybe, maybe not. The Gawler Craton versus Campana province. The Campana province probably formed in situ on the edge of the Gawler, and we could identify a number of long-lived and deep-seated structures throughout the northwestern Gawler region. So, we've seen this diagram from Stacey. I'm going to be using similar tools, which I've highlighted in orange, to address the problem of that northwestern margin of the Gawler. So I'll be using isotopes, potential fields, orthogonal deep seismic lines, and the OSLAM MT data. So we normally think of the northwestern Gawler as really data poor. Well, it might be at surface, but when we tend to look a little deeper, we've actually got a fair few things in which to constrain models. So epsilon hafnium plot may be a bit scary. So if we plot how rocks evolve from when they're extracted from the mantle, that evolves along where the trend of the red arrows goes. So now I've explained that, we can look at what the graph is showing. We can see that the pink, red, green, and blue plots are rocks from the Campana province, so they plot in quite a different space to Palaeoproterozoic rocks from the Gawler Craton. So we can clearly identify that there's a major boundary in between the two. It's compositional changes which identifies a real boundary. A structure just might mean there's a structure there. It doesn't necessarily have to be something different on either side, but we can clearly see they are quite different. So, okay, Gawler Craton to the southeast, Campana province to the northwest. Fine, we knew that already, but we've got a drill hole from the northern Gawler, which plots in the field of the Campana province. Okay, so that means either we've misdefined our arrays, or we've got our boundary in the wrong place. And we can tie rocks from the Campana province to have evolved from a mantle extraction event at around 2000 MA, and some work being done with more drill hole constraints from across the border in WA to say that some of these rocks might have formed from an oceanic source. So we've juxtaposed oceanic crust against continental crust at around about 2000 or 1900 MA. So how do we do that? Either we can subduct oceanic crust underneath continental crust and juxtapose the two that way. We can have a strike slip offset, so similar to what's currently known from the West African Atlantic margin, or we can have a passive or extended margin setting, so similar to what we've got in the Northeast Atlantic off the Norwegian margin. So we've mapped these trends out in isotopic space. Let's have a look in map view. So it's a similar data set that Stacey showed just a few minutes ago. So I'll just point out that blues on the map mean there's more mantle input to rocks sourced from these drill holes. Red on the map is more evolved sources, so more continental crust type affinities. So we can broadly see that in the Gawler Craton to the eastern side, we've got more evolved source, continental crust, we knew that already. Out in the Campana province, we're looking more juvenile. So we can start to identify where some major gradients might occur. So we're pretty poorly constrained because there's not a huge amount of drill hole data throughout this region, and we need magmatic rocks to get these sorts of results. So we've identified where a major gradient might occur in that sort of orientation. So what other tools can we use to investigate that? We can have a look at the mag data, aeromag, and we can see, okay, there's a whole heap of structures that we can interpret through this region, but which are the big ones? Which are the major ones which control this juxtaposition? We don't know. So the aeromag is probably imaging too shallow in the crust to identify something deeper seated. And in the northern Gawler, at least, the aeromag is probably imaging the marginal deeper center of the Noah domain metasedimentary rocks, which are showing with a high amplitude and generally short wavelength response. So that's, again, suggesting that they're fairly shallow. So what else can we try? Let's have a look at the MT data. Again, a common theme throughout these few talks. We can see, as Kate and Stacey pointed out, Gawler fairly resistive towards the core, and the Campana crust is fairly conductive. So again, there's something different going on between the two. We can also see a few zones within the Gawler itself that look like they are conductive and maybe a product of intracratonic reworking or major structures that have been hit by some fluid flow or magmatic events. So we can point these out. We've got in the purple line, we've got a gradient between what looks like resistive Gawler crust and to the more conductive Campana crust. And in the yellow line, maybe that's the zone of reworking. That also coincides with the Carrara shear zone. So put these back to some sort of schematic model. We can see maybe the Campana crust is the conductivities, the response of a thermal event not seen in the Gawler. Well, we kind of know that already. We don't see too much, if any, evidence of Musgravian type thermal event in the Gawler, whereas we do in the Campana and the Musgraves and that sort of thing. So that might be what we're mapping out there. And potentially with the Carrara shear zone, we're focusing fluid on a fairly major and potentially long-lived and early structure. So we've identified where these structures are. What can we do to have a look at the nature of what's going on throughout the whole crust, not just top, middle, or bottom? Let's have a look at them in profile. And the deep reflection seismic is a fantastic tool to do that with. So what I'm showing here is two sections just going across the cratonic margin from the Goma line at the bottom and the Euclid-Gawler east-west line above. So Macroscale, I won't go into detail of seismic interp because the screen's not good enough resolution to do that. Macroscale, we can see highlighted in the purple, we've got a fairly reflective upper crust associated with the core of the Gawler Craton. We've got a bunch of outward dipping structures which may indicate a reworked margin, and we've got a pretty bland non-reflective upper crust associated with something outboard. So we can then feed these crustal blocks back into our map view models and map out where these changes occur. So where we plotted the red arrows, which identify the gradients in isotopic data, MT data, all that sort of thing, plots just in our rework zone in the seismic. Kind of cool. And in map view, we can use potential field data to correlate between the two and remarkably consistent geometries. So we'll go back to our geometrical analogues. What sort of system can we try and tie this geometry to? So we don't really see any evidence of subduction. There's no deep reflectors dipping off into the mantle underneath the Gawler. So we can probably rule that one out. We've got major structures dipping outboard of a continental region, so we can maybe say, okay, a passive or extended margin might be more appropriate. And we don't really know too much about whether there's been major strike slip movement on these structures or not. We don't have the data resolution in terms of drill holes and offsets and that sort of thing to really define that. There may be quite a significant degree of strike slip movement, but we can't really define that. So if we were to tie an analogue in, that might be the sort of region that we're looking at. So again, a modern analogue will show the northeast Atlantic margin off the coast of Norway. It's been a lot done on this region in terms of investigating a passive or an extended margin, and we're seeing vaguely similar sorts of geometries. So this is an evolving model and fairly loosely constrained at the moment, but this is the sort of thing that we can try and present. So we can track the evolution from top left, maybe what it once looked like at around 1900 MA. Then we've got a marginal deeper center deposited on top, which may equate to the Gawler domain metasedimentary rocks, effectively obscuring what might have been this margin. And then we've hit that with a few orogenic events, the Kimben, the Kararan, and reworking at 1450 as well. And bottom right, effectively the geometries we see now. So outward dipping structures covered by metasedimentary rocks and sedimentary cover as well, obscuring what we see today. So to summarize, Gawler inboard, reworked margin dipping outboard, which is the contact with the Campana province. So go back to my key points. Gawler margin, we can say that not necessarily where it's been mapped. The original mapping was based on aeromag, and we're saying the change might occur inboard of that and at depth. We can suggest that the Campana province formed in situ on the edge of the Gawler, and we can clearly identify that there are some pretty deep and fundamental structures here across a 40 to 60k wide zone. As Stacey said, it's not appropriate to draw single lines, discrete margins between these sorts of cratonic regions. They've been reworked, hit lots of times. They're transitional zones, and they're pretty wide. And lastly, hopefully results from the Campana drilling program will feed into these sorts of ideas, tectonic concepts. Might get proven wrong, might support this model. We'll wait and see on that one. Thank you.